My name is Brandon, and I am here to talk about scaling SRE. This is Ship's journey as we built a site reliability team and a process that we created called Reliability as Code. This talk needed a little bit more doggos and kiddos. So I'm the director of site reliability at Ship. I've been with Ship since 2017. I've served in a number of different roles in the infrastructure org. From engineer all the way up to today. And prior to Shipped, I worked at Amazon Web Services for 5 years. I was in customer-facing roles from engineer to account manager to solution builder. And I got to really help customers of all sizes optimize their cloud workloads. But after 5 years, I kind of just got tired of talking about the cloud, and I just kind of wanted to do it myself, and I wanted to build and manage my own services and deploy them to the cloud. So I thought Shipped was a great startup opportunity, and it turned out to work okay. So I've gotten to watch as Shipped grew from a startup to a pretty big organization, and it was the Shipp's rapid growth that was a big part of what motivated us to build out the site reliability team and build products that scaled with our engineers and our customers. So there's a link app. Connect with me. We're hiring. Lots of stuff that we can be doing together. Currently at Shipped, our site reliability org is comprised of 3 separate teams. It's about 20 people today, and our teams are responsible for observability, resiliency, and incident response. Our observability team is focused on building self-service tooling for our developers to have the performance insights into their production workloads. Pretty basic stuff that you think of as an SRE team is our observability team. The resiliency team is in charge of measuring and improving how our infrastructure responds to change. That's a very intentional strategy for what we're doing with resiliency. And our incident response team manages our incident communication tooling and creates process around our incident management, incident command, escalating to stakeholders, communicating to other teams. It's a pretty broad response that that team is responsible for. Super proud of how our team has built these innovative tools and allowed us to manage the crazy growth that we've seen from a startup to an acquisition and then to a pandemic-fueled surge in grocery delivery. It was very wild over the last few years. So reliability as code, that's the terminology that we use internally that kind of describes the process, our strategy. It's pretty analogous to GitOps. A lot of the stuff that the Flux team was talking about was super exciting that we could definitely have some type of partnership with them. But it's an approach that allows us to scale the efforts of our team efficiently. And this is the important part, by enabling developers to own the operation of their own services. I have been a support engineer in the past, and I'm very sensitive to the fact that we are not support engineers. Developers can't throw things over the wall to us. We're software developers that build tools that allow our developers to have better operations on their own services. One other thing I want to talk about is best practices, in quotes. That's a term that I'm going to say a lot in this presentation, but I just want to kind of say that it's a term that I hold loosely because it's kind of like food preferences. There's definitely no best for every team. Do what works for you in the situation you're currently in. And what I'm going to talk about today is what's worked for us. All right, starting at the beginning. Site reliability organization at Shipped was established pretty soon after we were acquired by Target. We knew we had to build more reliable services and built a team that focused on that. At the time, we were starting to build we're trying to build a reliable product. It was not super reliable, and so we needed this team to help scale. Our first strategy was based on, this is a retroactive term, but individual heroics. It worked well when we had about 3 or 4 engineers. We were trying to just meet all the internal and external demands that we had from our customers. We moved from problem to problem, putting out fires, building dashboards, visualizing specific hotspots. Our lives are exciting, but time was not spent efficiently. So our customers were the loudest problem at any given moment. But it did have some pros. We all learned a ton of stuff. Not sustainable. Constant paging, lack of sleep. I think that's a good place for teams to start, but we did not want to stay there. So the next model we approached was the embedded SRE strategy. This is a recommended approach in some organizations. It meant that each product team had their own dedicated SRE that was available to help with observability and troubleshooting. So this SRE that was paired with individual teams would attend stand-ups, it would meet with the product teams, it would build deep relationships with their specific customers. But it also had pros and cons. We were able to shift left, so we were able to build reliability into our services more quickly. And we had great relationships with our developers. The cons, it does not scale sublinearly. It's one SRE to one dev team, and we just literally couldn't hire fast enough to build this out. And at the end of the day, we were pretty much doing the same reliability work as we always were. We were just the ones that were doing it for that specific team. So we knew we needed to scale our reliability in an efficient way. And over time, we decided to centralize our efforts and build tools that our customers could use to implement reliability best practices for their own services. Many of the tools we had already built required lots of manual configuration. This posed a problem for adoption. We really wanted our tools to be used by the dev teams, and we didn't want to be the ones that configured them for each of the teams. So we needed a scalable way for developers to implement our tools into their own applications. I really resonated with what Leslie said earlier today, is that these tools need to be self-service and they need to be simple for them to be adopted. And so we tried building this culture of observability that really helped us to get that adoption and help our developers apply the tools that we've built into their own infrastructure. So this is a strategy that we adopted based on the infrastructure as code model. And this is what we called reliability as code. So I'm not going to go into infrastructure as code too much, because I think I'm going to assume there's a base level of understanding at DevOps days. But I'm going to give a quick definition that shows some of the cultural tenets of infrastructure as code that I think are really important for our services and for best practice again. This came from an AWS white paper. Infrastructure as code enables the creation, deployment, and maintenance of infrastructure in a programmatic, descriptive, and declarative way. I think that's the most general and basic description of infrastructure as code I could find. And so I'll walk through a little bit of each of those points as to why it was appealing to us to build our tools in this way. We had a long history of infrastructure as code practices because of how critical they were to our rapid development and deployment models. So first, programmatic. Infrastructure as code allows your code to be treated as, it allows your infrastructure to be treated as YAML files. It can be copied and pasted, it's repeatable and scalable, it's version controlled, it's peer reviewed, and changes can be quickly rolled back because it's just code. Descriptive. Your code is described in a YAML or Terraform or other type of file, and so it's a great form of documentation. It describes how your infrastructure is laid out descriptively, and anyone else in your team can understand it pretty quickly. And it's declarative, so you can decide the desired state of your final solution, and the automation platform will determine the best way to achieve it. This is very similar to what we wanted in our own tools. So here is a very high-level summary of what the delivery internals look like at Shipped. We have a phenomenal DevOps org. DevOps in our world is different from site reliability. That's an entirely different set of engineers. But they've developed an amazing deployment pipeline process that's incredibly sophisticated and customizable for what we want to use. And this is really the biggest thing that allowed us to do this. Without this, we would not have had the opportunity to build our tools around this infrastructure as code pattern. So the tool that manages the delivery pipeline, the team that manages this pipeline, developed a webhook service that was affectionately called Captain Hook. That serves as the central hub for the GitHub and Terraform cloud events. Its primary purpose is to facilitate Shipped's internal deployment pipeline and aims to present a unified interface for all customers that want to take action on a merge event. So following this left to right here, when a developer writes code, submits a PR, and it gets committed to Git, that PR is pushed to a main or staging branch. Captain Hook publishes a message to a Kafka topic. And then our reliability as code services have consumers that listen for messages on that topic and then take an action when a relevant merge is detected. Our reliability as code services digest the payload of that message and query the repo, which is that dotted line. Our service then goes back to the repo of the service that was deployed, and we'll look for a corresponding YAML file that will provide information about specific reliability resources. Health checks, alerts, dashboards, I'll go into that in just a moment. So I'll come back to this in a little bit because it's a very high-level summary from an engineering leader's perspective of how this works. So here are the components that make up our reliability as code tool suite. We provision health checks that monitor each individual microservice. We have dashboards that are provisioned. They can be custom to a service's needs, but they are deployed out of the box once the service has been deployed. Alerts are extremely important for our reliability as code model. These are provisioned to ensure that each team has sufficient alerts to make sure that their metrics are being paid attention to. We also have the ability to run load tests as code. And finally, chaos experiments was the last thing that we've pulled into this model, where we can execute chaos experiments as code during a microservice deployment. So I want to jump into a little bit more detail about each of these. The first service that we wrote was the most necessary because it was most urgent to us at the time. And it followed the pattern that a tool created a synthetic health check for each of our services. We were beginning to lean into the concept of microservices at the time when this was developed, and we knew that we were going to need an automated way to ensure that each of our services was operational. The solution we created was to align the concept of health checks with each individual microservice. These health checks needed to synthesize the customer experience. This was not just a network ping request looking for a 200 response. This had to be more business specific. All services were designed for a purpose, and so we wanted to test that specific purpose. We wanted to make sure that our health checks were intelligent enough to examine the request payload as well. So if the expected value was not returned when requested, then we could tell there was a problem. We also want to make sure that these were highly configurable. We wanted to make sure that the health checks met the needs of the developers, and so the developers had to describe the specific requests that our health checks were making. We also knew it had to be scalable. We were about to experience a microservice explosion, and we did. We have probably 300 to 400 microservices now, and each of them have a corresponding health check, at least one, to measure the operation of that service. So to answer that scalable part, this was the solution we created. It provisioned our service, the health check service, provisioned AWS Lambda functions at scale. So each of SHIP's internal microservices had a corresponding Lambda function that would make regular requests to the corresponding endpoints. And these were provisioned with CloudWatch events, and they were invoked once a minute against all the services endpoints. So in our account right now, you can just check health checks in our production account, and each service will have at least one Lambda function that has a health check name associated with it. This is a small snippet of the YAML that's associated with the health check service. As an example, this is called monitoring.yaml. So each repo has a monitoring.yaml file that looks something like this. This is just one part of it. It's for the cart shelves service. And this workflow, really quickly, it's a request with a method. In this situation, it's a GET request. And it's a GET request against that URL, the v2 cart shelves endpoint. And you can pass all the parameters that you need for the developers to pass in. In this situation, these specific IDs that are corresponding to what the service does, this is going to be different for each service. And then obviously you can pass in headers, and then at the bottom it checks the response in the payload. And you can be very granular with this. You can tell if the response can be empty. You can tell if the key value is there. If any of these specifications are not met, then it will return an error, and we'll know quickly that something's wrong with our service. So going back to this, when you provision this custom health check, the developers have to create that YAML file, put it in the root of their service repository. Then as the services were deployed, Captain Hook publishes a message to that Kafka topic. And then our health check consumer digest that payload of the message, query the repo for the YAML file, and the health check will be provisioned through AWS Lambda. So this happens hundreds of times a day at any time a service is deployed. And that's the same model that we break down for each of our subsequent reliability as code services. Those are the Kubernetes steering wheels there, if I didn't say that earlier. The next tool that we built was one that provisioned Grafana dashboards. This was needed because Grafana has a very special place at Shipped because I think it's the only tool that all the engineers use. It's a great way to visualize your time series metrics, and I can't speak highly enough about Grafana. But at the time, it was very painful to provision all these by hand because each of these, even though you can represent dashboards as JSON, it still requires a lot of tweaking to actually get it in a useful state. So it just seemed natural that when you deploy a service, you get a dashboard out of the box that has all the metrics that you care about. And a little bit different, this but similar pattern. When a new service is provisioned, Captain Hook will post that message in a Kafka topic. Our consumers will read that message, create a new dashboard based on one of our predefined templates. That's important because that all of our services can have the same look and feel from service to service. It's not going to be a completely organic, completely unique service. It'll be one that has some similarities in the dashboards. It allows the dev teams to have a source of information out of the box, and it's also critical for SREs as well, because when a problem is happening, we can know exactly where to look to figure out which metrics are on fire, and it's just a helpful situation for both teams. The first thing that we knew we needed to do was implement the golden signals from the Google SRE book, which is a fantastic place to start. Start reading if you're building a site reliability team. These golden signals included request count, response time, error rate, and capacity. Google might have those phrases a little bit differently, but this is essentially how we broke it down into our world. And each of these dashboards has to be customizable. We knew that this was going to be helpful for engineers, but we knew that we weren't going to be able to predict all the requirements for what the engineers needed. So there is a way for the engineers to modify the Grafana template in their own account. And that way that when their service is deployed again, they'll have a custom panel or whatever else they need. So it'll be essentially a bespoke visualization that's maintained in the version control system of that service. And of course, it has to be version controlled. If someone makes a manual change to a dashboard, we want to make sure that the next time the service is deployed, that dashboard will be right back with the correct format. Next, alerts as code. This one is one of the extremely critical pieces that we're still implementing in the rest of our infrastructure. It's a very messy problem. Alerting was a very messy problem for our engineering team. So we had so many ways to create alerts, and all of them were manual. We had alerts created in CloudWatch, in Grafana, in our time series metrics. We had alerts created in logs and in our databases. And we had alerts that monitored infrastructure, monitored business metrics. And we had some alerts that monitored the dashboards that were displayed in our offices. The scope of our alerts was crazy broad. And what made it worse is that we weren't even monitoring the things that we needed to be paying attention to. Some services were deployed to production without alerts. And it just caused a lot of problems for the people that were on call. So we implemented alerts as code. We needed a way to ensure that all services had that baseline level of alerts, but we also wanted to do it along with the cultural tenets of our alerting philosophy. I mentioned earlier that we want the developers to own the operations of their service. So first and foremost, ownership belongs to the service teams. That's something that we really need to iterate as much as possible. If an engineering team has a service running in production, that team should be the one handling the alerts for their services. The second tenet is we have to treat every alert as actionable. If an alert comes to your pager, it should be something that requires action. And if there is no action, then you should delete the alert or modify the threshold. Corresponding, the third tenet is treat noise as toxic. If you get a lot of alert noise, my watch is paging me right now. The on-call engineer will become accustomed to ignoring these alerts, and you will develop alert blindness. It will impair your response time when real customer impact is being measured. So treat alert noise as poison is what a former colleague used to say. Lastly, manually created alerts are vulnerable to errors. So we wanted to make this a programmatic operational way that we ensured that as many opportunities for misconfiguration were removed. Our alerts as code service was pretty straightforward to implement, but we had to allow developers to describe the alerts the way they wanted them to be used for their service. So within their YAML file, they can define the metric, they can set the threshold of that metric, and they can set the time interval that's required to set the alert off. What I mean by that, I'll use another code sample here. These are 2 example alerts for a big important database. The first alert is set for CPU utilization. So if the CPU utilization metric in, I believe this was CloudWatch, if it exceeds 80%, then, if it exceeds 80% over 60 seconds for 8 out of 10 minutes, that's what the data points refers to, then it will trigger an alert and page the shopping cart team. And we also specify the priority of those alerts as well. And similarly, the next alert on the bottom half of the screen is for a bytes used for cache metric. This probably refers to a Redis cluster. So if the Redis cluster metric exceeds that very large number, 800 gigabytes or so, for a period of 60 seconds for 5 minutes in a row, then it will send a P1 alert to our shopping cart team. I don't think we have a database called Big Important Database, but this is a sample of what it could do. So, okay, that took away our observability needs. We solidified our alerts, we solidified our dashboards, and we solidified our health checks. So then we moved into our resiliency space, the team that measures and monitors our infrastructure for change. And so the resiliency team is responsible for our load testing service. Our load testing service currently extends Locust, which is a third-party tool that we utilize pretty heavily. It's a Python, the load test framework Locust is a load test framework that generates load based on Python scripts that emulate customer workloads. So when our load testing service receives a request to run the load test, it downloads the test scripts from GitHub repo of that specific service, and it generates load by invoking the locust command of the test name, the request per second, and the duration specified in the load.yaml file. So this requires two files. It takes the load.yaml file of our automation, and it takes a specific Python file that explains what type of locust test you're going to be running. This also allows us to enforce our testing strategy, where we want to generate amount of load to see it fail. We want to see exactly which point it falls over. We also want to test way more load than expected. This is a big part of our peak prep procedure. The Q4 is always a really big time for us, so we want to make sure that all of our production services are peak prepped, load tested as much as possible. And again, just like our health checks, we want to represent real activity, something that's way more than just simple GET requests. We want something that actually synthesizes customer activity. And lastly, our newest pattern was chaos as code. Our resiliency engineering teams were implementing chaos engineering practices for years. However, the way we were doing it required chaos game days to be run. Game days were great. They were super fun to do. It was really fun breaking things on purpose. But it takes a lot of overhead. I didn't really define chaos engineering, so maybe I should back up a little bit just in case you're not familiar with it. But chaos engineering is a practice of intentionally inserting failure scenarios into a workload to measure the resilience of the particular service or your environment. It helps to understand how your service can degrade gracefully and to build intuition for your engineers when specific components do fail. We started doing the chaos game days, but like I said, very manual, very large overhead. It took several days to prepare the experiments and then execute the experiments, and it was just a lot of overhead. So we decided to give that power to the dev teams. The chaos as code service is a pattern that is similar to our other load testing strategy. Devs specify the type of chaos they want. You can specify the attack that you want, and then you can run it in the YAML, the chaos.yaml file, and then let the fireworks fly. So, unfortunately, our chaos only attacks non-prod environments today. We're still trying to get our first chaos in prod, our first intentional chaos in prod. But one day that would be a really big win if we run a chaos test in prod. I'll be posting on all my channels about that. So we use two services to extend chaos today. Gremlin is a fantastic tool. It's very easy to get started. It has a great UI, a lot of integrations that work with Kubernetes and other cloud providers. And Litmus is a more, I believe it's an open source library that you can build chaos attacks around. And so what the chaos.yaml file does allows you to specify the target and the duration. This is a sample from our chaos.yaml file. The first example introduces latency into a Redis cluster. So this runs from the perspective of a service that talks to Redis. And you specify the attack type in the top argument. Then you specify the duration of the attack for 10 minutes, and the latency that we're adding should be 500 milliseconds. And we're applying that to 100% of the traffic. And then you just get slower Redis calls for 10 minutes, and you see how your server handles it. The second one is a lot more fun, the Redis black hole attack that completely wipes out all traffic. You specify the duration, and target percent of traffic, so you can kind of roll it out gracefully. But yeah, that will definitely break some stuff. I did mention, I think at least my slides mentioned earlier, that there are some downsides to this practice of reliability as code, or everything as code, is kind of like the way that we're heading. The biggest one is feedback loops are kind of long. It takes time for your YAML file to be deployed to your service, and then you don't actually know if your resources were provisioned the way that you expect them to be provisioned. So we're working on ways to shorten those feedback loops today. Also, there's very brittle API integrations. I'm just kind of being honest. When you build a lot of dependencies on third-party APIs, those APIs can break. If any contract changes, or if you make any significant migrations, if you change cloud providers, things are going to get kind of messy. So that's something that you have to keep in mind when you want to make a change to your infrastructure. And lastly, there's a learning curve, but all things have a learning curve, and we still think that this is the simplest way we could design it to make our developers understand how to emphasize our tooling best practices. So a little bit of practical help. We haven't released any of our tools open source yet, something that we've talked about. So this is just kind of an aspirational, we're definitely something that we want to do. We would love to get this out in open source from our lawyers, but for the moment, the advice that we have, start with CI/CD. That's a critical component to making all this possible. Next go to infrastructure as code. It's super important to make sure that you have declarative structures in your software that provision infrastructure and infrastructure resources like this. If you don't have coders, hire coders. If you don't have coders, you can train coders. You have to emphasize coding skills in the process and emphasize coding skills in learning and development. I am really thankful that Shipt has such a great L&D process where we can spend a lot of time learning new technology and getting to play with things that are new and exciting. And the last point, know your customers. Our customers were our developers. We knew what they wanted. We measured that through adoption metrics, and if some service of ours does not get the adoption metrics that we're hoping for, then we talk to them and figure out what would make it more appealing to get them to use it. Right? Thank you, guys. Thanks for the talk. Thanks for your time.
Ooh. All right, anybody have any questions for Brandon? They want to ask from the, look behind me too. Oh, you got one question. Here you go.
Great talk. So far, as always, I can say that confidently. Does Shipt have a platform engineering team? You mentioned a DevOps team that was separate, and I was curious, how you draw a line between DevOps and reliability and platform.
Yeah, that's a really great question. I kind of glossed over that. When I started, we were all platform engineers. I think I was the third or fourth platform engineer. Then we decided that was way too much responsibility. So the strategy that we moved into was building a reliability team that focused on the stuff I mentioned, and a DevOps team that focused on CI/CD and infrastructure provisioning. So that might be the platform team you're talking about. But now we have so many more. We have a DBA team. We have a security team. We have we have the incident response team and the resiliency team. So everything I talked about was dependent on that DevOps team to really do that work. And a large portion of people are here today that built it. So definitely don't want to take the credit for that.
All right, any other questions? All right, well, thank you, Brandon. All right, give us just a